So for this, we're investigating the relationship between the period and length of a simple pendulum, and we're going to use this to work out the acceleration due to gravity. First thing is we're given this information here, which is the length of the string, and we're given the time. Big mistake can be made here is that it's the time taken for 25 oscillations. What the experiment is showing is the period, and the period involves just one oscillation. So that's just something should jump out at you first. The pendulum used consisted of a small heavy bob attached to an inextensible string. Why was a small heavy bob used? So it would act like a point weight. Easy to find the center of mass. Another reason would be that it would be aerodynamical. Small bob would not be affected by wind, like maybe if we were to use a ping pong ball or something like that. It would be affected more by air around it. So it's a point weight, easy to find the center of mass. And to find the center of mass for that bob, you can use a vernier calipers or a micrometer, if you want to, just in case. Why is a string inextensible? Well, it's very important that the length remains constant. So we want the length to be constant. The length is not constant. This equation won't hold for the period of oscillation. Describe how the pendulum was set up so that it swung freely around a fixed point. Now what that means is that it needed to swing in just one plane. So we want our pendulum just rocking back and forth, not moving with a bit of circular motion. We want it just going straight back, straight forward. And we do that using either a split cork, so that this string can fit between the split cork, but the split cork will just ensure that it stays in the same plane. So the plane of oscillation doesn't change, remains the same. The next thing that we're asked is another precaution when allowing the pendulum to swing. Well, you could say that you don't want drafts in the room because drafts could affect it perhaps. A more important thing would be that you release the pendulum and you do not give it a push. By giving the pendulum a push, you'd affect your results. So, this is critical. That you need to be able to work out the length exactly. So it's from where the oscillation starts to the center of mass of the bob. From where the oscillation starts to the center of mass of the bob, you have to be very clear in showing that it's to the middle and not to the end or the start of it. The next point is to draw a suitable graph to investigate the relationship of the period of a simple pendulum and its length. What is this relationship? And justify your answer. Okay, this is the data we're given. We're given the length in centimeters. And we're given the time in seconds, but that's the time for 25 oscillations. So we have to divide each of these by 25 to find the period of oscillation that we're going to be using. Divide by 25, all of them. We should also move our decimal point for the length back to 2, so we're using meters, 0.4, 0.5, 0.6, 0.7, up to 1 meter. Now, here's where you should look at the equation for the period of oscillation of a pendulum. It's equal to, T is equal to, it's equal to 2 pi times the square root of L over G. Okay, now in order to show the relationship between the period and the length, it's nice if we can plot them as a linear graph. Now in order to do that, we have to get rid of this square root sign here. Now, we get rid of that by squaring both sides. So we get t squared here is equal to 4 pi squared times 1 over g times L. I've just split that up a little bit. So all we did was square both sides, and now we've got t squared is 4 pi squared times 1 over g. Now what I want you to think back to is our equation for a line, which is y is equal to mx plus c. If this relationship holds, what we will put on the y-axis is the period of oscillation squared. What we put on the x-axis is the length of the pendulum. And then what we should find is that we'd be able to get a line, we'd be able to pick 2 points, work out the slope, and that slope should be equal to 4 pi squared over g, and from that we can calculate g. So, from here, the first step is we square the tensions. Now, not the tensions, the periods of oscillation. Now, the first is, so there's 2 operations we have to do here. Divide the times by 25, so 31.3 divided by 25 is 1.25, and that goes so on there. And square those numbers, which gives us the t squareds of 1.572, and so on. The next operation is that we're just going to be putting L on the x-axis. So we can see that now in a second. We've got a graph paper here. I'll just put a couple of points in just to prove that they are a straight line through the origin when you plot t squared times L. So to do that, let's have a look at our first point there is 0.4, and our t squared is 1.57, so it's 1.57 and 0.4. It'll be somewhere about there. The next point is 0.5 and 2.01, so that'll be somewhere about there. And if I just even join those 2 lines, those 2 points there, we'll be able to see. Now you should do all the points first. Those 2 points, all the rest of the points will end up close and to this line here. So plot all the points, fit a best fit line, and then if it's a straight line graph through the origin, it shows that the tension squared is proportional to the length of the pendulum. And finally, you can calculate the slope of that line and use that to work out g.